In the last two sections of Chapter 5, we're going to consider the concepts of maximizing power to a load and in doing source transformation. All of this is using the Thevenin equivalence or the Norton equivalence of a circuit. So in section 5.4, we're at the top of page 73 in our ECE 301 workbook. Suppose we were given the Thevenin equivalent of a circuit, in other words, indicated by the left side of the circuit here. So we have the Thevenin voltage, we have the Thevenin resistance to these two open terminals. But suppose we were wiring or connecting to the Thevenin equivalent a load, in other words, another resistance. And our goal was to determine the maximum power that can be delivered to it. How much power can be delivered to, say, this heating element that we might connect to it, all right? And so what we've done here is gone ahead and connected that load to it, and now we have a new circuit. We have a closed path here. We could use a mesh current, call it I sub 1, that flows through these three elements that are in series, and start off by saying, let's look at a relationship of voltage using KVL. We're going clockwise here, and again, if we just go around clockwise, we come into the negative polarity of the voltage source, so we'll represent that voltage minus VT. Then we're going to assume PRC here, so the voltage by Ohm's law would have to be that resistance times the current. All the currents are the same, I1, and then we'd add the same similar component here for the voltage through the load that we're adding, and sum of those equal to 0, right, from KVL. Then algebraically, if we were to solve for the mesh current, it wouldn't take too long to show. It's just this simple fraction. It would be the Thevenin voltage divided by the sum of the two resistances, okay? Now, if you remember our power calculation form, how to calculate power, a couple of different formulas. One of them would be using the current. We would square the current and multiply by the resistance to get the power of that load, all right? So again, we have the resistance of the load and the current flowing through it. By a substitution, in other words, then what we could do is say, well, we now have a representation for that current in terms of the Thevenin voltages, Thevenin voltage and the resistances in the circuit, and we plug that in and square the terms, all right? So we now have a function. The power function is given in terms of the variable R sub L. So R sub T is like a fixed constant because that's whatever the Thevenin resistance is, and same thing for VT, but now we can see we have a nonlinear function involving R sub L. And the goal was to find the value of that resistance that maximizes the power function, right? So what we'll do is use our calculus skills here by just saying, well, if it's a function of this independent variable R sub L, let's just take the derivative of that function, set it equal to 0, and finding those roots will tell us the value of R sub L that will yield the maximum power, right? And that's exactly what we're going to do here, right? So we'll first of all just write down the power function. Again, the independent variable is R sub L. And of course, we could change the variable name if we wanted, but we'll leave it as it is there. And the function that we're trying to find the maximum of, again, is this one, the Thevenin voltage squared times R sub L divided by R sub T plus R sub T plus R sub L quantity squared, okay? All right. So that's just, you know, and you can see that it's definitely nonlinear because this is a constant plus R sub L squared. This is another constant times R sub L numerator. Just to make things easier in terms of not having an overload of subscripts here, let's make a variable substitution. Let's let A, the constant A, be VT squared. Again, that's just a constant. It doesn't change. It's the Thevenin voltage. It doesn't change. And let's do the same thing for the Thevenin resistance. And let B equal the Thevenin resistance, right? So again, R sub L, just so it is by definition, this is our independent variable, okay? For which we are taking the derivative with respect to, right? So in this case, the function then is power function in terms of R sub L. It's just A times R sub L over the quantity B plus R sub L squared with our substitutions, okay? All right, and if we want to rewrite that for purposes of taking derivative, we could write that as A times R sub L, and then pull this up, pull that denominator term up, and then change it to a negative exponent, right? Just for the purposes of taking derivatives. Okay. So calculus 1 here, go ahead and take the derivative of that power function, all right? Keeping in mind that what you're going to have to do here is the product rule, because R sub L is not a constant, it's an infinite variable. So we could write this as, let's say, the first times the derivative of the second. So we'd have A times R sub L times the derivative of this second term here. So again, there's two terms here. So the derivative of the second term will be minus 2, right? Quantity B plus R sub L, that changed the exponent to minus 3. And then taking the derivative of what's inside the derivative of R sub L with respect to itself is 1. So you don't have to worry about adding any multiplicative term there. Plus the second term times the derivative of the first there, right? So in this case, we would have the second term, B plus R sub L to the minus 2 power times the derivative of the first part, right? And that's A times R sub L, so that derivative is just A, okay? Right? And what we can do now is maybe clean this up a little bit. So what will we have here? So we will have minus 2A times R sub L all over the quantity B plus R sub L to the third power is the first part. And the second term would be a plus A over quantity B plus R sub L squared, right? And again, maybe simplifying this in terms of getting a common denominator. Clearly, this has to be the common denominator. So that's going to be our common denominator term. And so we'll have to multiply this one top and bottom by another B plus RL. And what we should get is something like this, minus 2A R sub L plus A times the quantity B plus R sub L all over B plus R sub L to the third power, okay? All right, so that's the derivative. And then what we want to do now is set the derivative equal to 0, because we know from calculus the maximum or min will occur wherever the derivative is 0. All right. Now, if we set this equal to 0, clearly we cannot have the bottom be 0. So this means that we'll say if we're setting the derivative of this power function equal to 0, that's going to imply that the numerator's got to be 0. So the minus 2A R sub L plus A times B plus R sub L has to equal to 0, right? Denominator can't be 0, right? So, but the numerator would have to be 0. And we could, that implies we could factor an A out, and we'll have A times minus 2R sub L plus the quantity B plus R sub L equal to 0, okay? All right, but remembering what A is, if we come back up here, we remember that A is nothing but the Thevenin voltage squared, and we're going to make the assumption that that is not 0. So assume, because we have no voltage, we're not going to be able to generate any power, right? So let's assume that A, which is equal to VT squared, is not equal to 0. So therefore, what must happen is, for that derivative to be 0, therefore what we must have in this minus, the other part has to be 0, minus 2 times R sub L plus the quantity B plus R sub L has to be equal to 0, okay? Just simple logic there. Okay, and then what does that really say? All right, so if we collect some terms here, all right, so what that says is that you got a minus, so that means minus 2 times R sub L plus R sub L plus B equals 0. Well, that's a negative 2RL, and that's a positive 1, so you're going to get negative 2RL. Pull it over the other side. That tells us that what R sub L has to be is equal to B. But what is B? Oh, yeah. B is the Thevenin resistance, okay? So that tells us where maximum power occurs. So we'll write that down. So the power function, when you hook that load to your Thevenin equivalent, is maximized for the case where the load you add is equivalent to the Thevenin resistance. So That's very important. That tells you if you have the Thevenin equivalent, you'll maximize power to a load of the same ohmage that you have with your Thevenin equivalent, all right? That's the only way it's going to be maximized, okay? If you really wanted to compute the max power, so let's suppose we wanted to compute it. What is the max power? This tells us when it occurs. What is the max power? So we'll say the max power, then we have to plug in this choice for R sub L. So the max power that we're going that can be delivered to the resistance, right, is what? P of R sub T. In other words, you should put in the Thevenin resistance. That should be what's attached to the Thevenin equivalent. In this case, the power function would just give us what? VT squared RT. Again, I'm just substituting in the original power function. I'm switching L for T there in the subscript. That's going to be over, you're just going to get twice R sub T quantity squared, okay? And that's going to turn out to be what? VT squared over 4 RT, okay? Or somebody could write it this way. It's possible you could write it this way. It's take half of the Thevenin voltage and square it and divide that by R sub T, okay? I mean, either formula here is fine. It's just this might be a way of just looking at it in terms of the original parameters VT and RT. That is the max power possible. Right. So when does it occur? When the load you connect to your equivalent has the same resistance as the Thevenin equivalent, and that's how much power is going to be generated. VT divided by 2 squared over RT. Okay. Alrighty, so the last section of this chapter involves what's called source transformation. This is section 5.5. We're now at the top of page 74. And so this is a very handy technique sometimes that you see people in circuits analysis use. It's very possible to replace a voltage source in series with the resistance by a Norton equivalent with the in which the current source is in parallel with the same resistance. So this is the idea that maybe it would be very useful sometimes in being able to analyze a circuit, getting desirable voltages and currents, if you could flip a source into the other form. In other words, flip the Thevenin equivalent, flip it into the Norton equivalent, or vice versa. Now, I mentioned this in the last lecture, so we have to be very careful here. These are the equivalents, all right? And the relationship between this Thevenin equivalent over here and the Norton equivalent over here is given by this formula, that current source is just the ratio of this Thevenin voltage to the resistance. So the resistances are the same here. This is in series with the voltage with respect to these open terminals. And in this case, the resistance is in parallel with the current source. And again, notice that when you're in series, this resistance is connected to the positive pole of the voltage, and the current direction here is always going to be in the direction from matching the ordering here of the polarity of the voltage. It's very important to make sure if you have plus minus like this, the arrow goes up. If it's minus plus, suggesting that it's delivering the energy down, then you've got to switch the arrow. This is indicating very clearly that the current flow needs to come up through the negative pole here so it can deliver energy into the resistance. So it makes sense that the arrow here should match it by pointing up, okay? So you just have to be careful that you orient it correctly. So we're going to apply this technique of switching out sources using different equivalents by 2 examples. So we're going to look at example 6 now. And what we're interested in doing is finding the 2 currents there, the one flowing through the 5 ohm resistance and the one flowing through the 10 ohm resistance. Again, these are not in series because of this other conductor coming in and an external current, an independent current source coming into it, all right? So we know from KCL that we're going to have, they're not going to be, there's going to be more than one current there. So what we're going to do, though, is we're going to transform this current source into a voltage source, all right? And by doing that, all right, we'll be able to use KVL, all right, and just apply voltage equations through, and KCL as well from YouTube. But we'll use KVL immediately to get one of those currents, right? So the first thing we have to do is figure out, our goal is to switch out this current source. So we've got to look at it from the perspective of a Norton equivalent being converted to a Thevenin equivalent, all right? So let's do that off here on the side. So the box that's on page 74, we're over on the right-hand side. So we're looking at this Norton equivalent of 1 amp, which is in parallel. Now it needed to be in parallel, absolutely, okay? So we'll call the top terminal A. I'm kind of just flipping it over here, just flipping it over. So I have the 2 open terminals and I have the 10 ohm resistance here, okay? All right, so this is our Norton equivalent, I'm abbreviating. What we need to do is represent its Thevenin equivalent and then replace this Norton equivalent with the Thevenin equivalent in the original circuit, right? So we know that the Thevenin equivalent will have to look like this, all right? There's the Thevenin voltage. And again, it must be the same resistance. So there's no calculation needed for the Thevenin resistance. This is R sub T, we know that, okay? So we have R sub T already there. The only thing that we've got to figure out is, again, this is the Thevenin equivalent I'm doing down here, is we have to figure out what VT is, right? Well, remember, as the top of 74, there's the equation of connection right there, and I'll write it again. So the connection is the current source of the Norton is always equal to the ratio. That's sort of an ohm, basically it's kind of Ohm's law applied to these 2 equivalents. I sub n has to be the Thevenin voltage divided by the resistance, right? So in this case, another way of writing that is that VT has to be I sub n times R sub T. And you know what I sub n is, it's given to you as 1 amp. So VT has to be 1 amp multiplied by the Thevenin resistance, which is 10 ohms. And so therefore we immediately know that VT must be 10 volts, okay? Right. So this is equal to 10 volts. And now what we'll do is we're going to redraw this circuit with the Thevenin, excuse me, the Norton equivalent you see on the right-hand side will be replaced with its Thevenin equivalent, okay? So, and then everything is of the same type. All your sources in this case will be voltage sources. So this is the idea of source transformation. It might be easier to have all your sources of the same type, okay? So here we go. You'll still have the 5 ohm resistance here. Now you have to be a little careful here how you connect it up, all right? Because this 10 ohm resistance was in parallel, right, with the 1 amp source. Now that 10 ohm resistance has to be in series. So when we flip this diagram over, you should have the other resistance here. So we'll have 5 ohm, 10 ohm, correct? And this comes down into a 10 volt source, okay? Again, that Thevenin resistance needs to connect to the positive pole, right? So there we go. We still, in this case, we have certainly 1 mesh current. Everything is in series now, and we'll call it I sub 1. But before I continue, I hope this is clear. Taking the representation of the Norton, flipping it to Thevenin, and then replacing it in here, just making sure we reconnect it correctly, right? So what's happened is the Norton equivalent is replaced here by the Thevenin equivalent. That's what we've done, right? But now we could do KVL very easily because we have all voltage sources here, and we can find the voltage representations using KVL, the other resistances. We'll go KVL clockwise, and we'll come into the negative polarity of the 10 volt source. So we'll have minus 20 of the 20 volt source, we'll have minus 20. You would have a 5 ohm resistance times the mesh current I1. Then you would have 10 ohms times I1 as well, correct? And then you'll come in the positive polarity of the 10 volt source from the Thevenin equivalent, right? So that is equal to 0. See how fast this is? It's beautiful work here. And then this is 15 I1 has to be equal to, you have minus 20 plus 10 will give you negative 10, and then you pull it on the other side, it'll be a positive 10. So that just says I1 must be 2/3 amps, right? Okay. Right. So that's telling us that this mesh current now we have the answer. We're trying to say, well, what is the current coming through the 5 ohm resistance and the 10 ohm resistance of the original circuit? Okay, so we have the fact that the current coming through the 5 ohm resistance, which is this is the same 5 ohm resistance in the original diagram, is going to be 2/3 amps, right? Okay, now, if we're saying, well, wait a second, is this I2 the same as this I1? No, this is a different current, but this current, or in other words, this situation here is equivalent. In other words, we have found out from this voltage source, this is the mesh currents flowing inside here. This is the current through the 5 ohm resistance, which is the same 5 ohm resistance here, right? This is in series, and these two are not in series here. So we can't say, oh, well, wait a second. So this means I1 must be equal to I2 as well. No, these are completely different, right? So you have one of the currents. This current here is the same as the I1, right? But this I2 is not the same as the I1 because clearly these are not in series, okay? So what we'll have to do here is go back to the original problem, the original circuit, and here we can do KCL. Say top node with the original circuit. Okay. Again, this is kind of like our network analysis. You have to be careful where the currents and the relationship between the currents and the resistance, where they make sense in terms of where you're at right now. And right now, this current makes perfectly good sense to go through that 5 ohm resistance. And the same thing would happen here, but not over here. This resistance is not the same configuration that 5 ohm down here, right? So KCL on the top node suggests immediately that, well, we know if we write outgoing currents, we'd have to have minus I1 plus the outgoing I2 minus I1 equals 0, because I would be doing KCL here on the top node, right? So we know that this relation is always going to be true to start with. We just had to figure out how to get one of them from some other form. In this case, we got it from the KVL, okay? All right. So this relationship with KCL tells us immediately that I2 has to be equal to I1 plus 1. So therefore, I2 has to be 1 2/3 amps, or 5/3 amps. And that's what the problem asked for. Okay. So again, changing one of the sources might allow us to get this KVL equivalent. Now, the reason good motivation for doing this, because we don't know what the voltage is here. So if you were making an attempt to do KVL around this loop, you wouldn't be able to do it because we don't, remember the voltage of a current source is not predetermined. We don't know that, okay? So, but by converting it to a voltage source using the Norton equivalent, now we know exactly what it is independently. It has nothing to do with the rest of it. It's independent, it has nothing, depending upon what's going on in the rest of the current. And then we can just do a KVL like we normally would. So there's one advantage of doing source transformation. Okay. All right, let's do this one more time in 2 parts. Okay, so we're going to do this in 2 parts for a different problem at the top of page 75. We want to solve for 2 currents again, right? And we're going to do it in 2 ways, right? In the first way, you can see the configuration we have. We have 2 different sources of 2 different types. And the first approach we're going to do is convert the 2 amp current source into a 10 voltage source, all right? Again, what we've got is we'll go ahead and do the calculation, but we're going to take the Norton equivalent over here. So the Norton equivalent is here. We have an independent current source of 2 amps that's in parallel with a 5 ohm resistance. Noticing the configuration, it's pointing down, all right? We know the relationship always is that VT, remember, is equal to IN times RT, okay? And we know this is 10 amps. We know the Thevenin resistance is 5 ohms. And so immediately we know the Thevenin voltage is 10 volts, okay? The question is how do we draw it? Well, we need to draw it so that the current direction to deliver energy is down. So this is the way we'll do it. We'll flip the polarities, put plus minus that way, right? We know it's 10 volts, right? Can you remember how we should configure the resistance? Should we connect it to the negative polarity or the positive? You're absolutely right. We should always connect it to the positive like we've always had, okay? So again, if this is AB, this is AB, okay? Matching that, right? Okay, so those are two equivalents. Again, pay attention to the alignments. And now what we're gonna do is replace this Norton equivalent with this Thevenin equivalent down here, okay? So when we do that, what will we have? Well, goodbye 2 amp source, hello 10 volt source, minus plus 10 volts, correct? And then we have the 5 ohm Thevenin voltage down here, Thevenin resistance here, 5 ohm here. It's connected in that fashion. Up here we'll have the 10 ohm, and then this will come into another, but notice the difference in polarities. You have two 10 volt independent sources, and you can see clearly if you think about the flow here of the current to get PRC going here, we'd want to come out here, and so if the current is flowing into the negative term here, it's going to generate 10 volts for this resistance. So its voltage polarity, this must be plus minus, and then the same thing will happen down here. Or this will be reversed, and this will be plus minus. But that's not what we need to do now, is do a KVL. Okay. So we'll do KVL, let's say anti, or if you like, counterclockwise. In England, we would say anti, but we'll do either way, counterclockwise. So just to draw it, what we're talking about is we will go this way, okay, with our KVL loop, right? And let's just call this mesh current I2, just for the sake of being different, but not too different, because the reason why I'm going to represent it I2 is kind of like we had before, where this current representation will be the same as the I2 that way, okay? So I'm going anti-clockwise because I'm trying to match out the current coming through the 10 ohm resistance. So this is the same current coming through the 10 ohm resistance, right? Because remember, these two components are now equivalent to these two, right? So this current is still the same current, I2, right? Nothing's changed from the perspective of this resistance. This was the current coming through it. This is still the current coming through it, coming out of the 10 volt source into it, you see. The rest of this is independent because we switched it out, right? So this is still I2. So let's do KVL anti-clockwise on this particular circuit here. So let's say we come into the negative, coming into the negative polarity of that voltage source, so we'll get minus 10 volts. I'll just say minus 10 volts. Then we will come into a 10 ohm resistance, assuming PRC, 10 I2. Then we will come into the negative polarity there, minus 10, and then plus 5 times I2 again, okay, equals 0. And you've got negative 10, negative 10 is 20. And again, you're going to have 15 times I2 equals 20. Or what you'd have is that current I2 has to be 4/3 amps. Okay? Right? Again, it's very important that we understand that in writing this mesh current, it's the same representation as that current there from the perspective of the 10 ohm resistance. Okay? Just referring back to the other problem we had a minute ago, just so that we keep it clear. The same thing happened here. From the perspective of swapping out this current, we will represent from left to right the current coming from the 5 ohm resistance. this part of the circuit that we added has no difference. This is the same current, right? That's coming from the 10 volt into the 5 ohm resistance. So that's why this current and those current are equivalent. So we can do a KCL now, right, on the top node. And so if we do a KCL now on the top node of the original circuit, so let's go to KCL, top node, original circuit, meaning up here. What relationship do we have between our currents? Well, we could, if we want to represent them as, we could do it outgoing or incoming. It doesn't really matter. So maybe we'll represent them as, let's just for once represent them as the sum of outgoing. Sometimes it's helpful just to, make a mention of, how we're doing it and how we're representing it. So if we do the sum of the outgoing currents is equal to 0, then we have certainly 2 going out, we have I1 going out, and we have I2 coming in. So this would have to be equal to I2, right? So another way to say that then is that we're trying to solve for I1 here. So I1 is equal to I2 minus 2, right? So therefore, we would have to have this to be 4/3 minus 2, which is the same thing as 4/3 minus 6/3, and so we would get a minus 2/3 amps. So in other words, the current I1 is minus 2/3 amps, okay? Now, what's interesting there is the fact that the I2 value here was 4/3 amps does indicate that we have the correct reference direction for I2. But notice what happened with I1 being negative 2/3 amps. So the reference was from top to bottom, but actually the current flow is from bottom to top. It's interesting. So this current, which kind of makes sense to some extent, this current 2 amps is being split either up through the 5 ohm resistance or over here to the 10 volt source there, right? And so this current I1 direction really was reversed. Okay, so that kind of makes sense, right? So the last thing I want to do is do the same problem, but maybe we'll keep everything as a current source, right? So again, doing source transformation, we're still targeting I1 and I2, but we'll change the 10 volt Thevenin equivalent into a Norton equivalent, okay? So, and if we do that, again, we know what the relationship is in terms of IN, remember, has to be the Thevenin voltage divided by the Thevenin resistance, okay? And so in this case, we are switching out this 10 volt Thevenin voltage. So that says IN has to be 10 volts divided by, in this case, 10 ohms, which is the Thevenin resistance in this case. So again, what we're dealing with here is this voltage source, 10 volts, with a Thevenin resistance of 10 ohms, okay? So this is the Thevenin equivalent, okay? And we're swapping it with a 1 amp Norton equivalent. So the Norton equivalent must look like this. 1 amp going up. Remember, the Thevenin resistance is in parallel now, okay? And so this again is 10 ohms, okay? So this is our Norton equivalent, and we're going to swap that in, all right, for this part of the original problem, okay? So let's redraw the circuit. You still have the original 2 amp source, direction arrow down. You still have the 5 ohm resistance here in parallel. But now we have another parallel resistance, which is 10 ohms, connected to, and again, be very careful with the direction arrow. This one has to point up. Notice the differences in the direction arrows. It's also 1 amp and it points up, okay? Right? Now, let's think about what we're interested in finding, all right? So from the perspective of the current flows, remember the direction of the original I1 current was this way, I1, okay? And what we can do now is try to figure out what that current is. Now notice I'm not trying to label this current because this doesn't exist from the original, from the perspective of the original circuit. We have swapped this part of the circuit out completely, right? But we left this one alone, so it's still the same I1 current representation. Can we figure out what I1 would have to be? Well, if you remember current division, what we have here is this 1 amp currents. We have a division of the current, say in this top node, splitting out, right, between two resistances, right? So what we've got to represent here is how we could use CDP effectively. And remember, the way we do it was to take a proportion of what the source would be, right? So, so a couple of things to think about here is, all right, what is the representation of the current that comes in and flows out through the, we have a 5 ohm resistance here, and we have a 10 ohm resistance here. So we have to be careful. You've got two amps coming this way, 1 amp coming this way, all right? And so we know that from the perspective of KCL, this top node has got 1 amp coming out, it's got 1 amp coming in, right? So the net change we have is negative 1 amps here, which is going to be distributed. I know this is a little bit tricky here, but we have to be careful here to say that, all right, so again, you could also say, I'm representing the sum of the outgoing, the sum of the incoming has to be equal to 0. So this has got -2 coming in and a +1 coming in. So it's a net coming in of -1 amp, right? That's distributed, right? You'd have -2 from this side and you'd have a +1 from this side, okay? If this wasn't here, it would just be -2 being distributed out. But because you have this one coming in, the net difference is always got to be represented. So the net current flow from the top node down has got to be -1. And that -1 gets distributed into the 5 ohm and into the 10 ohm. Okay? I hope that makes sense. This is just KCL applied, that the net incoming is the net incoming current. The top node, okay? So from CDP then, I1 is distributed by its neighbor's proportion over the total resistance, which is 5 + 10, times this -1 amp net incoming current, and that would give us -2/3 amps, which is the same answer we got earlier, okay? Same answer, just checking to see if the logic makes sense. And then doing KCL again, top node, original circuit, which we already know, right? We already know that the relationship is that I1 has to be I2 -2, or in this case, I know that I2 has to be I1 +2. In this case, it's 2 - 2/3, which is 4/3 amps. Okay. So I think the only tricky part of this problem probably is this concept right there, that again, with CDP, you're taking a source, a current source, and you're trying to distribute it across parallel resistances. And in this case, we can't just say it's 1 amp, because if we, given the direction this is 2 amps down, if we reversed, if we wanted to represent this as an incoming, we'd have to change the sign, and then we'd have -2 amps coming in and a +1 amp coming there. We have to represent the differential in that, okay? So that just shows you that you can do source transformation to either keep voltages the same, or you could keep your sources as current sources, either way, okay? So that concludes then our discussion of using these Thevenin and Norton equivalents in unique ways for maximum power, or in terms of doing our network analysis approaches, but switching out Norton and Thevenin equivalents.